Okay, well, good afternoon. Let's give a warm welcome to Andrew Steiner, who's currently an associate professor at the University of Tennessee. So Andrew received his PhD from Stony Brook University and then actually got the APS dissertation prize for that year in nuclear physics. He then went on to do postdoctoral work at the University of Minnesota, Los Alamos National Lab, Michigan State University, and then finally at the Institute for Nuclear Theory at the University of Washington. So yeah, Andrew's been at the University of Tennessee since I think 2014. He got a career award from the National Science Foundation. And what was kind of unique, it was jointly funded actually by the physics division and the astronomy division for his joint work in neutron stars. So yeah, Andrew's an expert in the field of neutron stars, and I think he was really one of the first to start using sort of these robust statistical tools to infer nuclear physics properties from a wide range of neutron star observations. And so he's going to tell us, I think, some of that today. So welcome, Andrew. And
oh, thank you. Thank you very much. That's very kind. Can you guys all hear me okay? Does this work? Okay, so now I want to, I tested this earlier. I just have to make sure that the computer recognizes that I'm operating on the, okay, good. So thank you very much for having me. So this is my fourth time to the area. I visited Commerce a couple times and also here at College Station in February of 2020, right before COVID. It's excellent to be back in the area, and I hope to be back a lot soon. So I want to talk today about the nature of hot and dense, strongly interacting matter. I want to acknowledge for the particular work that I'm going to discuss today, I have many excellent collaborators who have participated in this work. In particular, I would like to highlight my postdoc here, Zidu Lin, at the University of Tennessee, my graduate students, sort of current and previous, Anik, Spencer, Xingfu, and Satyajit, and then undergraduates, Jesse and Hema, who are currently working with me. So these, along with my other collaborators around the world, deserve a lot of credit for what I will present today. Please feel free to ask questions at any time. I'm certainly happy to accommodate and make sure that there's enough time for all the questions that you have. So I will begin with an introduction to neutron stars, of why they're interesting to me, why I think they might be interesting to you. I'll talk about neutron star mass radius curves. I'll explain that and the relationship with the equation of state of strongly interacting matter. And then I want to talk about the composition of dense matter from neutron star cooling. And as you all know, LIGO detected the merger of two neutron stars. And so in order to interpret that observational data, we need to do neutron star merger simulations. So that's a short way of saying neutron star mergers, because there are two of them, right? Okay. And so I want to talk about the new nuclear physics input we're generating for those simulations, and a little bit about NP3M, a new NSF focused research hub, and then I'll summarize at the end. Okay. So first, an introduction to neutron stars and their relationship to nuclear physics and or strong interactions. But first, what is a neutron star? In stellar astrophysics, the mass of a star determines its fate. So stars, so there are approximately three classes, and I have three pictures here. These three pictures are not apples to apples. These are different wavelengths. This is an extreme UV picture of the sun. So this is my representative picture for stars less than about 8 times the mass of the sun. These objects become white dwarfs in the end, okay, after they finish nuclear burning. There's this mid-range between about 8 and 20 times the mass of the sun represented. This is an optical image. This star here is actually 16 solar masses. And these stars will become neutron stars. They will go through a core collapse supernova explosion and then become neutron stars in the end. And finally, we have the very massive stars, which will become black holes. This particular object here is 33 solar masses, and this is too large to make a neutron star, and this will be a black hole in the end. So there's white dwarfs, neutron stars, and black holes. And so I tell people I'm an astrophysical gerontologist. I study old stars of this particular kind. So what are neutron stars? Neutron stars are just sort of quasi-spherical stars, principally composed of neutrons, yes, but also protons and electrons, okay? I also like to think of myself, in addition to a neutron star scientist, as a nuclear structure theorist. My favorite region, mass region, is the 10 to the 57 nucleon mass region. So there are approximately 10 to the 57 neutrons and protons in a neutron star, and this is one of my favorite nuclear physics laboratories. So neutron stars are much like planets. They have an atmosphere, a solid crust, and a fluid core. Okay, the atmosphere consists principally of light atoms and nuclei. The outer crust here, very quickly, as you move towards the center of the neutron star, the electrons become relativistic and leave the nuclei, and so we leave the atoms, and we're left with nuclei and then a sea of degenerate electrons. Then in the inner crust, it becomes energetically favorable for some of the neutrons inside nuclei to leave the nuclei. And so we have nuclei plus electrons plus neutrons, which happen also to be superfluid. And then in the outer core, as we transition from the solid crust to the fluid core, at these densities, it becomes no longer energetically favorable to make nuclei at all. And so we just have a soup, if you like, a fluid of neutrons, protons, and electrons. And the inner core is the big question mark. I don't know what's in there. I don't think anybody does yet. So this is one of the big mysteries. They're about the mass of the sun and maybe a few times bigger than College Station. Okay. So one of the holy grail questions, what is the composition of the core? Or another way of asking that question, which in the context of modern theoretical physics, is what are the degrees of freedom for the effective field theory, which best describes matter in the neutron star core. So this is what the question I would like to answer. I cannot answer this today. We're going to make progress, just a little baby steps of progress towards answering that question. Okay, so I've explained to you neutron stars and a little bit about their structure. Now I want to connect them to nuclear physics. So one of the ways to do this is through the neutron star mass radius curve. So I mentioned planets. Well, unlike planets, neutron stars are somewhat uniform. To a good approximation, almost all neutron stars in the universe lie on one single universal mass radius curve. Okay? And so we don't know what the true mass radius curve is, but this is just pretend like it's this for a second. And you see that there is a maximum mass. So stars above this maximum mass must become black holes. And all the neutron stars lie somewhere here on this curve. This low mass tail is fictitious. It sort of ends right here. I plot this for reasons which I'll make clear in a second. So Einstein's field equations from general relativity give you a one-to-one correspondence between this universal neutron star mass radius curve and the equation of state of strongly interacting dense matter, the equation of state of these neutrons, protons, and electrons. And of course, at low densities, the nuclei. So in the context of this particular one-to-one correspondence, what is relevant is the pressure as a function of the energy density. You'll notice I'm ignoring the temperature. This is because neutron stars are degenerate objects. The temperature, at least for this particular problem, doesn't matter, and you can assume that it's zero. So this is just the T equals 0 equation of state. The idea being that, of course, in laboratories like here at the cyclotron, we learn something about the nature of matter at low densities, but we don't know so much about the equation of state at high densities. On the other hand, if we have observations of neutron stars, if we can simultaneously measure their mass and radius, we'll put little dots. We can connect the dots, take advantage of Einstein's field equations, this one-to-one correspondence, connect it to the nuclear physics and learn something, the equation of state of neutrons and protons, the equation of state of strongly interacting matter. This idea has been around already since 1959, before the observation of neutron stars. Okay, so already at this time, people were thinking about sort of ways of understanding the nuclear Hamiltonian. Okay, and so this is a long-standing problem, and I study neutron stars in particular because they give us the insight into the nucleon-nucleon interaction, which we might not be able to discover otherwise. One way of seeing this uniqueness is to look at the QCD phase diagram. So here, on the x-axis, we have the baryon chemical potential. You can think of this just as a proxy for density. It's monotonically related to the density. So this is low density and this is high density. Of course, the baryon chemical, quarks just have a third baryon number. So there's just this factor of 3 here. And the y-axis is just temperature, which you're all familiar with. So neutron stars occupy, they probe this region of the QCD phase diagram, the phase diagram of strong interactions at high density and low temperature. And this is relatively unique. Relativistic heavy ion collisions, lattice QCD. So hadrons are here. The virial expansion is here. So neutron stars are somewhat unique. And so this is one of the reasons why they're a good way to learn about QCD. Of course, you know about experiments here and other places which probe nuclei, and this is at slightly lower density, but also lower temperatures. So one of the important things that we were learning about, in particular because of the LIGO observation of neutron star mergers, is simulations of neutron star mergers show that these mergers may achieve larger temperatures up to 100 MeV. And this is an interesting challenge for those of us who study neutron stars, but also an opportunity. A challenge because this region may probe into the quark-gluon plasma. This may mean that in order to effectively describe neutron star mergers, we need to use quark and gluon degrees of freedom to describe them properly. On the other hand, it's an opportunity because maybe then using mergers, we can learn more about the quarks and gluons that we wouldn't have been able to learn otherwise. So, of course, you guys know there's a lot of work here on nuclei, on nuclear matter, and also on the quark-gluon plasma. And so it's an interesting connection between what I do and what you guys have a lot of experience with. So that's the end of my introduction. Are there any questions before I move on? Okay, so feel free to interrupt. So now I want to talk about the neutron star observations in the equation of state. For the moment, setting the temperature equal to 0. So I would love to show you pretty neutron star pictures, but I can't. They're too small, and the pictures look boring. There's like one picture, and it's like a dot. And so instead of showing the neutron stars, I will show you the globular clusters that the neutron stars are in. These are prettier. So in each of these, there's 1 or 2 neutron stars, which we use to determine the equation of state. So 47 Tucanae, these are all globular clusters. And the important thing from the astronomy perspective is that globular clusters provide us a measure of distance. Distances are difficult to measure in astronomy, but if we know distance and we measure, the flux and the effective temperature, we can get the radius. And so this is the idea of how you use neutron stars inside globular clusters to measure the radius. And it turns out you can also get a little bit of mass information as well. So this is the data set, and then you connect the dots. And so we will do that here in a second. But also, if you know something about neutron star radii, it turns out you can learn even more, because as I mentioned, we're all thinking about the neutron star mergers. And so when 2 neutron stars get close to each other, as they do in a merger for a short period of time, they tidally deform each other. And so that deformation, the extent of that deformation is that tidal force is due to the tidal deformability. I like to think of this, I just call it squishiness. If the neutron stars are very squishy, when you bring another neutron star nearby, it deforms more significantly than if it wasn't squishy. Okay, so another way of thinking about this is the gravitational analog of the nuclear electric polarizability. If you bring an electric field close to a nucleus, it polarizes. Okay, it turns out that if we can do this, if we can measure the radius of a neutron star, we also have information about the tidal deformability, because the tidal deformability is correlated with the radius. Easy to think of. If the neutron star is big and sort of fluffy, then it's very squishy. If the neutron star is very compact, everything's very dense and there's a small radius, then it's not very squishy. Okay? That's the intuitive way to think about that. So in 2015, knowing that we had observations like this, neutron star radii, and knowing that there's correlation with the tidal deformability, and hoping that LIGO would eventually detect a neutron star merger, I attempted to predict the tidal deformability. And so I computed this. I should say we, of course, this is a team of us together. We computed this quantity called lambda, which is related to the tidal deformability. And I'm in the nuclear physics world, but I like to play nice with the astronomy people, so I use CGS units. And this is this 10 to the 36 grams centimeters squared second squared. And so this is the result of our analysis is somewhere between these two distributions. It's either here or there, somewhere between 1, and 3, maybe smaller, maybe a half, and 3 times 10 to the 36 in these units. So that was cool because we had a prediction of the tidal deformability. So obviously I will get to the LIGO observation, but before I do that, some other things happened in 2015. One is, again, because because we have this information from neutron star observations on the neutron star mass radius relation, we wanted to generate a new equation of state for use in neutron star merger simulations in 2015. And so this equation of state, I'll talk more about these kinds of equations. This is now a finite temperature equation of state, you remember, because mergers probe 100 MeV, so now I have to think about temperature. It's not just pressure and energy density at T equals 0. So we created a new equation of state called SFHO, okay? And so some of our colleagues used this equation of state in a simulation of neutron star mergers. This is particularly important because neutron star mergers may be the source of R process nucleosynthesis. Heavy nuclei are created in the universe one of two ways, by the R process or the S process. And one of the putative locations that the R process might happen would be a neutron star merger. Okay, so a Japanese group led by Sekiguchi et al. I was not directly involved with this. We just calculated this equation of state. They did this simulation, and they found that R process abundances weren't impacted by the new equation of state. We did nothing to change the R process distribution. However, one thing that did change is the amount of mass ejected in the merger. This is cool because if you have more mass ejected, that means more R process nuclei from each merger are ejected out to the interstellar medium. And this means that mergers are a better source for R process nucleosynthesis if you use the SFHO equation of state. So, of course, this is an early part of a very long story. There's still a lot of uncertainty here. I will tell you later in the talk about how we are trying to tackle these uncertainties. At least in 2015, it appeared that it might be the case that these equations of state improve the ability of neutron star mergers to produce R process nuclei. Okay, so now fast forward to 2017, the neutron star merger. I use these observations to predict now. Okay, so I'm going to talk about LIGO. LIGO chose uppercase lambda, and they ignored CGS units. They went to a unitless version. So it's slightly different, but it's the same thing. Okay. There's just a simple numerical factor, but they predicted, they actually observed lambda tilde in their neutron star merger, and they verified the prediction. And this is the LIGO paper, and where they say, look, their 95% upper bound begins to compete with the value derived from X-ray observations. Okay? And so this is cool because not only did LIGO verify the approximate tidal deformability, which we measured, but they also got evidence that from a actual kilonova, an electromagnetic signal from GW's 170817, which offered some support for neutron star mergers as an R process site. And so this was cool. And so then, of course, I wanted to combine the electromagnetic observations with the gravitational wave observations of neutron stars and put them together to form a coherent picture. And this is now what we like to call multi-messenger astronomy, using photon observations and gravitational wave observations together. So we did that, and I do Bayesian inference. This is just these Tolman, Oppenheimer, Volkoff equations. This is just the form of Einstein's field equations that we use, and many of you may know Markov chain Monte Carlo. This is just a particular numerical technique, and so this is the results that you see for the neutrons. This is that universal neutron star mass radius curve. Okay, so I'm going to explain. There are 8 panels, and I'll explain why. So there are 4 different rows, and this is just our way of teasing out the impact of different data points. So you can focus on the basically the bottom row, which is the entire data set. Okay, and then there's the left panel and the right panel. Okay, or the left column and the right column. So you can see there's a qualitative difference between the left and the right, and what this is because this is many of you may have heard of Bayesian inference. This is, you can think of this as a difference in the prior assumptions built into the model. Okay, so that sounds kind of like a hazy statistical thing, but in this case, this comes from an actual physics thing. There's something really physical going on, and that is that the reason these two have a different slope is because there are different assumptions about the probability of a phase transition inside neutron stars to something, for example, like deconfined quark matter. And so the largest uncertainty, now I'm showing the equation of state plots. Remember, there's that 1-to-1 correspondence. So this is the pressure as a function of energy density. The largest uncertainty, whether or not, so it's really easy to see in the mass radius pairs, which it's more difficult to see in the equation of state. It's the difference between this sort of feature here and a different feature here. But the largest uncertainty is the presence of a phase transition. And that tells us that, yes, we're learning about neutron stars, but there are still some unanswered questions. And this tells us what those unanswered questions are in physics terms. So what is the solution to this? Well, more data. And in particular, the analysis of more data, the acquisition of more data, a tighter connection with the nuclear physics data, with astronomical observations. No amount of statistical wrangling is going to answer this question for you. Okay? This is, of course, this is something I've been doing for a little while, but in terms of this particular analysis, LIGO will eventually put me out of business. This is a very nice position for, at least for the country to, and the world to be in, because we hope that in the near future, LIGO gravitational wave observations will eventually map out this equation of state to much better accuracy than I can do. That's okay, because there's a lot more to strong interactions than just the equation of state alone. And so there are a lot more questions. We want more. We want to know what is, for example, the neutron to proton ratio. I said neutron stars are mostly neutrons. That's true. But how many protons are there? Is it 49%? Is it 1%? This can make a big difference. We also would like to know about transport properties, about how neutrinos and photons flow through the neutron star, about viscosities, about superfluidity. Okay, so and all of these things are manifestations of the underlying theory of strong interactions at QCD. So now I want to tell you how we're going to get at start to get at the composition. Okay? I can't tell you again. I can't tell you right now the correct degrees of freedom, but for baby steps, we're going to look at the neutron to proton ratio. So how does this work? Well, we start with, as I said, more data is the answer, and so this is a different data set, a different set of neutron stars. I'm going to explain to you what these are. So these are just isolated neutron stars. They're created in a core collapse supernova explosion, and all they do is cool. They're created at some high temperature, and after about 10 years, because the thermal conductivity is relatively large, almost the entire star is at one temperature. So the description of the cooling, this isn't the actual, okay, we do something more complicated, but the easy way of thinking about this is just this specific heat of the neutron star times the derivative of the temperature with respect to time is equal to the luminosity. All it does is lose energy by the emission of photons and neutrinos. And so as a result, the temperature decreases. For the moment, in order to simplify this problem, we're going to assume only neutrons and protons. Okay? We have to start somewhere. And so if we observe the luminosity or the temperature, and we observe the age, then we can watch the neutron star cool watch the population of neutron stars cool as a function of time. So how do you measure the age of a neutron star? Well, it turns out that you can do this through observations like this. This particular neutron star is not in our data set for other reasons, but it's a really cool picture and it very effectively demonstrates the point. Okay, so this is the so-called cannibal pulsar. So you can this is the neutron star here, and this is the supernova remnant. Okay, and so you can estimate the velocity of the expanding supernova remnant, and then track this back to the center, and then you know that the age of the neutron star is just the time it took to move from here to here. Okay, and so this is when you can do this, this is the most effective way of determining neutron star ages. Okay, and so these boxes are the data, you know, a subset of the data as of a few years ago, and so you have luminosity on the y-axis and time on the x-axis. And so you can see these theoretical cooling curves go through the attempt to go through the data. And so what we're going to do is use the data to determine the neutrons to proton ratio. Okay. So so how does the physics work? Well, so we know about beta decay. Astronomers are sort of as bad as everybody else at naming things. They have a new name for beta decay. In the context, they call it the direct Urca process. It very efficiently cools neutron stars because the neutrino is created and it just leaves. Okay, so this is an old plot, but what you see, this is sort of no direct Urca, and you see with direct Urca. Okay, so there are few stars down here, and most of the stars up there. That means beta decay is not operating inside neutron star interiors. So and one of the possible reasons that this process may not be operating is because it's a degenerate system. And so energy and momentum conservation constrains this process to be allowed only if the proton to neutron ratio is greater than about 11%. Okay. But obviously it's ruled out by observations, at least not all neutron stars. So there must be some neutron stars which have very few protons. On the other hand, if you take most theoretical models, your garden variety theoretical model from nuclear theory, and you try to construct the proton ratio, you almost always find protons there, in particular larger than this critical threshold. So there's a real quandary here. Why are there, what's going on? Why are there no neutron stars down here? Do they have few protons or many protons? So one of the potential answers to this quandary has to do with superconductivity and superfluidity. And so one of the ways I like to think about superconductivity is the historical context. So superconductivity was discovered in the early 20th century. And so you see this is year on the x-axis and the critical temperature is on the y-axis. There's this I've stolen from a master's thesis. Well, this has now been adapted from the master's thesis from PRA. But so you see over time, we're getting to higher and higher critical temperatures. Okay, mostly the recent records in high temperature superconductors happen because we're moving to higher pressures and higher densities. Okay, but this is laboratory superconductivity, which is mediated by, for example, lattice phonons. Okay. Now, if we think about superconductivity in the context of QCD, we obtain an entirely different picture. Okay. So we take all those data points and we put them on the same plot, but now we add QCD pairing. It's a completely different story. All the electronic systems are down here, and here are the QCD systems. So much larger critical temperatures. This is really high TC superconductivity. Already Bohr and Mollison and Pines in the 50s knew that pairing was important for nuclei. There is an interesting 1977 paper which suggested pairing between quarks. And there, of course, Ralph Rapp has an important paper about quark pairing in 1998, which significantly modified the estimate for this critical temperature, along with one other famous publication. In the context, so of course, now as I mentioned, we're going to specialize to only neutrons and protons. So there are three relevant superfluid or superconducting gaps which might solve this Urca quandary. There's the singlet 1s naught pairing. There's the singlet proton superconducting gap. And there's the triplet neutron superfluid gap. So this is a calculation, quantum many-body calculations of this singlet neutron gap. Okay, and there's about a factor of 2 theoretical uncertainty. This is at relatively low densities. In neutron star interiors, the situation is much worse. Basically, we can't trust any of the theoretical results to within several orders of magnitude. Okay, at least that's my claim. So it turns out that this triplet neutron superfluidity is the most important. And so we choose a particular phenomenological model to describe this, and then we put it inside our neutron star cooling simulations. So what are the results? We do find that not that dissimilar from previous nuclear theory models, that the proton fraction is large, ostensibly allowing for the direct Urca process. But what the data analysis suggests is that triplet neutron superfluidity pervades the star. That is, most of the neutrons are in this triplet superfluid state. And that superfluidity solves the Urca quandary because these neutrons are now paired. In order to decay into a proton, they would have to break the superfluid gap. That the breaking of the Cooper pair requires an energy cost. Those familiar with condensed matter will know that's just twice the gap energy. And so because they cannot pay that cost for the low temperatures, they cannot beta decay. So this tells us that yes, the proton fraction is large, but the neutrons are also superfluid. This is important because this is a constraint on the composition of the neutron star interior, which we wouldn't have been able to get otherwise. And I will point out that the proton fraction, this is something I intend to pursue in the future, is that, of course, the proton fraction is connected to a quantity which many of us know and love, the nuclear symmetry energy, and to heavy ion collisions. And so effectively, we are determining through astronomical observations the high density part of the nuclear symmetry energy. Okay. So let me just check time. I want to make sure I don't. Oh, good. We're good. Okay. What time do you want me to end? Yeah. Okay. Good. So we're learning using neutron star observations. We're learning something about the nucleon-nucleon interaction. We're learning something effectively about QCD. So what we would like to do is continue this logical inference. Our neutron star observations tell us about these constraints on the nucleon-nucleon interaction. We'd like to take that new nuclear physics knowledge and propagate it back to the astrophysics community, in particular for improved simulations of astrophysical processes. And then hopefully, if we have a better description of neutron star mergers, we can know more about, for example, our process nucleosynthesis. So in order to do that, one of the things which we need to be able to do is analyze the gravitational wave signal that we might be able to detect in the future after a neutron star merger has occurred. So of course, if the remnant is a black hole, then there's not so much signal. But if the remnant is a hypermassive neutron star, then there's an associated gravitational wave signal, and we can take advantage of that to understand the nature of the remnant. But in order to do that, we need simulations. We need good astrophysical simulations based on real nuclear physics input. And my claim is that the current nuclear physics input is not sufficient to accurately describe the post-merger remnant, nor to properly quantify the associated nuclear physics uncertainties. This is a problem, okay? And it's a problem we need to solve now before we get the data so we can interpret it properly. And so we're making progress, and I want to tell you about how we're doing that. So as I mentioned in the SFHO case, we are generating, now moving back to finite temperature, but between 0 and 100 MeV, we're creating equation of state tables. And so the parameter space, there are 3 axes, one just number of baryons per unit volume, temperature, and then you can think of the proton to neutron ratio, okay? Or equivalently, because electrons provide charge neutrality, the electron fraction. Okay, and so what I mean by an equation of state table is I need to tabulate pressure, entropy, neutron chemical potential, proton chemical potential, all the quantities as a function of these 3 variables. And so this has been done for about 30 years. There are various numerical codes and tables out there which provide this thermodynamic information. So most of the calculations to date have employed the same kind of paradigm. You take some fundamental, or phenomenological nucleon-nucleon interaction, and you just extrapolate it everywhere. Okay? And so what we've chosen is a slightly different approach. Is said, look, there are several inside this 3-dimensional parameter space. There are several different physical regimes. And so we use different models and different regimes, and then we quilt them together, hoping that we can obtain a more accurate description of the equation of state over a large range of densities and temperatures by doing so. So what I'm going to explain is several of these different physical regimes and describe just in words the kinds of models we're using. So the first is isospin symmetric, just equal numbers of neutrons and protons, matter near saturation. Well, you guys know how to do this at the cyclotron. Laboratory nuclei very effectively tell us about this kind of matter. Okay, so in particular, the nuclei SIDAC collaboration is very good at analyzing nuclear structure data and determining the equation of state or an effective nucleon-nucleon interaction as a result. And so we use those results. Okay. For neutron-rich matter, obviously nuclei are not extremely neutron-rich. So it turns out to be better to use nuclear theory results. Neutron matter is very easy to calculate in terms of a quantum many-body system. So we use, for example, the results from Stefano Gandolfi. In the non-degenerate case at low densities and high temperatures, it turns out all we need to use are proton-proton scattering phase shifts. Using the virial approximation, you can determine the equation of state directly from these phase shifts. So this is what we do. For dense neutron-rich matter, well, those are neutron stars. We have a lot of experience with neutron star observations, so we know how to do that. The other physical regime which is important is hot matter near nuclear saturation. So as Jeremy will tell you in more detail than I can, the quantum many-body theory of zero temperature matter and finite temperature matter is a little bit different. It's easier to use different methods. And so I've been using Jeremy's results for several years to describe the equation of state at finite temperature matter near the saturation density. Okay. So we put all of these things together, except there's one thing missing, okay? And that thing missing is the nuclei, the nuclei which occur at low densities. And so we need to put those nuclei in as well. And so one of the cool things that this Cyclotron Institute here has done is determine information from clustering in low density matter, okay? And in particular determines, for example, this ratio, the number of alpha particles divided by the neutron and proton density squared. And previous work has shown this is Matthias Hempel has sort of reprocessed and analyzed the cyclotron data plus several theoretical models available on the market and shown that as a function of baryon density, the experimental results are in this gray band. Well, those obtained here, I believe. Is that right? Oh no, the experiment is the right here. Oh, and yes, and there's a gray band. And then Matthias Hempel generated a theoretical method of describing this data, a way of arranging neutrons and protons into nuclei. And they pioneered this work in 2010. And so Matthias has shown that their theoretical method matches relatively well the experimental results obtained here. Okay, so actually Matthias is the H in SFHO. And so this is the collaboration which originally we used. And so we are still using this exact same theoretical approach because we know it works. Okay. In our new equation of state tables. So now we have descriptions of matter in 5 different physical regimes, which represent, laboratory experiments and astronomical observations, plus a verified description of nuclei and their coexistence with neutrons. And so now we have equation of state tables. So in addition, one of the things we can now do with this model is uncertainty quantification. Now, not only can we tell you the free energy at some particular point in density, electron, proton fraction, and temperature, but we can tell you a probability distribution for what the free energy is. So this is exactly the Helmholtz free energy density per Helmholtz free energy per baryon at one particular density, electron fraction or proton fraction and temperature. And you can see we have a probability distribution for that. And not surprisingly, our previous results, SFHO, are somewhere inside that probability distribution. And so we've also generated a 9 sample equation of state tables. They're about 300 megabytes, 500 megabytes. Just download them, and then you can use them in your favorite neutron star merger simulation. Okay. And one of the things we're currently doing is extending this uncertainty quantification to the neutrino side, making sure that our neutrino cross sections also have this uncertainty quantification. So this is just one small part of a larger research frontier that's important, across the world in understanding neutron star mergers and what they mean for nuclear physics. And I obviously cannot do this by myself. Not even a team of 2 or 3 people can do this, because we need connections. We need people who can simulate neutron star mergers. We need multi-messenger astrophysics people. We need people familiar with nucleosynthesis, people who do finite temperatures, like people here who study quark gluon plasma at high temperatures. We need experiments, and we need to put this all together. And so the NSF has given us $3 million in a focused research hub called NP3M, the Nuclear Physics of Multi-Messenger Mergers, combining several different people, including Jeremy Holt and Ralph Rapp here from Texas A&M, in order to attempt to make progress understanding exactly the nuclear physics of neutron star mergers. And in particular, my vision is that you could imagine expanding, and there's historical precedent for expanding focused research hubs into physics frontier centers. And this might be a good place to do that. So just to summarize, let me check to see. Oh, good. Okay, I should go quick. I only have 2 minutes. We leverage neutron star observations to learn about QCD. We obtain constraints on the universal neutron star mass radius curve and the equation of state. We understand a little bit about where the uncertainties come from. We know something about the neutron to proton ratio, and we're taking this nuclear physics input and we're putting it back into the astrophysics simulations, and we're using NP3M to do that. So that's what I've talked with you about today. In addition, there are other things. If you would like, you should certainly feel free to ask me about. I have a little work on Bayesian decision theory, trying to optimize experimental designs in order to maximize information gain. This is kind of fun. We have a Hoyle state-like prediction for resonance in carbon-carbon fusion, and there is some exciting work here that Phil is doing on this. I do a lot of Bayesian inference, a lot of statistical inference, and in particular, one of the things that we're realizing is the importance of generative statistical models in order to do more faithful descriptions of our problems on the statistical side. And I'm using machine learning and neural networks to enable this kind of nuclear astrophysics. So that's all I have. Thank you very much for your time. Right. Yeah. Okay. So for the Zoom people, so Jimmy and Ko asked about how I describe high density matter and whether or not I use I can describe quark gluon degrees of freedom. So currently, right, sorry. Oh, I see Ralph first. So okay. Oh no. Oh no, don't do that. Okay, fine. Okay, so in principle, the information from neutron star observations, which I have put here, could accommodate quark and gluon degrees of freedom because it's just a direct parameterization of the pressure versus energy density. However, one of the things that we are doing which is important, is putting explicit quarks and gluons in here, in part because it doesn't matter so much from the equation of state point of view, but it matters from the neutrino opacities, because as you know, neutrinos scattering on nucleons and neutrinos scattering on quarks are different things. And so actually one of the ways this is happening is through this, I didn't mention this today, but this MUSE's collaboration is working on this problem. And I think that's probably the best way for us to work on that now. Hyperons I will do. Yes, that's that is a next step. That's not something I'll leave to muses. That's something I'll try to do myself. Yeah. So we'll see how quickly I get there. That's a good idea. Yeah. Can he talk?
Okay, yeah, I have a question. I didn't hear anybody calling on me. Should I go ahead?
Yes, please.
Okay, can you go back to the phase diagram you showed in the beginning? One of the kind of fundamental questions in the context of the diagram is actually the development of a first order transition. So at mu equals 0, we have a crossover at 155 or so.
Yeah.
And then, so this is kind of a fuzzy region. And then it actually is expected or conjectured that as you go up in mu, it develops into a first order transition with a critical point.
Right.
And that I would say is really one of the fundamentally most important aspects of the hot matter that is created in mergers, and to see if there's evidence. It can also be done with heavy ion collisions at somewhat lower energies. My question to you is that you mentioned that in one of your equational state that you have constructed that there's a first order phase transition. A key question is at what temperature that is. You mentioned superconducting temperatures, and indeed the predictions can go up as high as 100 MeV, and you know, that's really an open question. You can have gaps of 100, 150 MeV at 0 temperature. So where in your example that you mentioned does the critical temperature slot in, or the first order line?
Okay, so unfortunately for the particular work which I've described today, none of the models very effectively describes the transition between nucleons and quarks at high temperature. The early stuff that I talked about in the talk is T equals 0, and the later part of the talk is explicitly only neutrons and protons. There's a transition between maybe superfluid neutron matter and normal neutron matter, but unfortunately there's no transition to quarks yet. So I have done some work, as you probably know, on the transition between quarks and baryons, and I would like to revisit that, and I hope that the Muses collaboration will do some of that. And so I think I'll just say that I think that's a very important avenue for future research for NP3M Muses and all of us. Yeah. Okay. You're right. I didn't. So this lambda is the unitful one, and the capital lambda is basically is dividing this by mass to the 5th power, and then putting in a couple factors of the gravitational constant in order to make it unitless. But where this comes from, I think the way to think of this is you can think of it as a it's because of the second squared, there's probably the best way to do this is to go back to the geophysics case, because Earth has a love number, has a lambda also, and so I don't know the non-relativistic equation, but I will send it to you, because it should make sense of this unit system. Yeah. There's a 5th power of the radius in there. The second squared is baffling me a little bit for right now, but there's a way to do it. You have to put in either speed of, for the general relativistic problem, you can put in the speed of light. but it's probably better to go back to the terrestrial system and to make sense of that. So I'll have to send that later. I don't have that on the top of my head. Yeah, so so what we did for this particular work is I didn't want to redo the work, so I just used I used the posteriors of somebody else's Bayesian inference. And in particular, these people used charge radii, binding energies, odd even mass differences, and some fission information. They did not use any of the PRX information, for example, neutron skins. And they did not use anything about the electric polarizability, any information from giant resonances, GMR, GDR. So the PREX uncertainties are pretty large. And so if you add 40 binding energies, you'll never see the PREX results because the binding energies like squash the PREX error bars. On the other hand, the resonances, I think, may be more important. And this is a big part of one of the things I'm trying to do now, not the monopole, the dipole, but the gamma teller resonances. Because those are super important for me. And so yeah, it's a good idea. Right. Yeah, so there's so first you can the softening of the equation of state provided by the first order phase transition naturally decreases the radius and decreases the tidal formability. However, as you know, this signal is not unique. In addition, there is so what you can do is you can attempt to sniff out the quarks from the post-merger remnant. So there's a series of gravitational waves emitted by the post-merger remnant. You can do the Fourier transformation, look at the frequencies, the fundamental and the harmonics, and you can try to map that to what you know about quarks versus nucleons. I don't think the recipes for doing that are a little uncertain. And this is one of the things I would like NP3M to be able to do if we can. Critical opalescence is great for the critical point where all these correlation functions diverge. I'm not sure how that critical opalescence would come about in this case. I would have to think about that. That's a good question. I think right. Yeah, so this is exactly it's a slow process, so it is indeed adiabatic. But the entire neutron star, almost the entire neutron star, is isothermal, and so it's almost at one temperature, and so it just cools, and the temperature changes, and so it's sort of in astronomy we think of this as sometimes as Kelvin-Helmholtz evolution. The idea is it's a quasi-static. You move from equilibrium state to equilibrium state. Things being in a strong equilibrium, but not in the radiative equilibrium, if you like.